Welcome to Talkcast and to the second part of my discussion of Chapter 9 of The Fabric of Reality, Quantum Computers. Last episode, I indicated that this would be a two-part process of getting through this chapter, but I've had to revise things. Last chapter I spent rather long on exposition and very little time on reading, and I think something similar is going to happen this time, so it's going to be at least 3 parts in order to get through this chapter in its entirety. And as I said there, this chapter, more than any other in The Fabric of Reality, could itself be turned into an entire book, given the spectrum of topics that it covers, all the way from the differences between quantum theory and classical physics, what quantum computers are as opposed to classical computers, the nature of mathematics, the history of computation itself, all the way through to things like chaos theory and whether or not chaos theory really obtains in the real world, and we're going to be dealing with that in short order. So rather than a long intro here, let me get straight into the readings. This section of the book begins with David writing, and I quote, "In 1982, the physicist Richard Feynman considered the computer simulation of quantum mechanical objects. His starting point was something that had already been known for some time, without its significance being appreciated, namely that predicting the behaviour of quantum mechanical systems, or as we can describe it, rendering quantum mechanical environments in virtual reality, is in general an intractable task." End quote. So here we have David giving credit to Richard Feynman. There is some debate, of course, about the history of quantum computation and who is most responsible and so on and so forth for the field, developing the field. Of course, it is always a group of people that come together, but there are giants that stand out in the same way as we talk about classical computation as being Babbage and Lovelace and Turing and Church, and different people contributed different aspects of the solution to the problem of how to go about constructing these real-world things. Many of us seem to converge on the idea that it was Turing simply because Turing put down in fine detail, precision, a mathematical representation of what this device would be able to do. And in fact, what the physical operation of the thing was, of course, he didn't understand paper, as we like to say, but he had this idea of a machine which would be able to do the task of any other machine. So he had the idea of a universal machine, the universal Turing machine, which is the precursor, of course, today, the theoretical precursor to the physical objects that we have on our desktops called computers. But of course, there are others there. There was Babbage early on, who was manufacturing devices, and there was Church, of course, who had his own approach. And so when we get into quantum computation, then there is some debate about, well, was it Feynman who first came up with the idea? Was it David Deutsch who came up with the proof for the existence of these things? And many of us like to say, well, in the same way that we give Turing most of the credit for classical computation, we give Deutsch most of the credit for quantum computation, because, hey, he wrote the paper which explained how we can have the marriage of these two things, computation, hitherto thought of as nothing but an arm of pure mathematics to a large extent, certainly in the academic realm, and quantum theory, unifying these two things to give us the theory of computation. The theory of computation today is, of course, quantum computation, and David will come to that. But that aside, that's just an interesting part of the history of ideas for those of us who are interested in that kind of thing. I think the books for the history of quantum computation are yet to be written, but I've seen some attempts at people writing books about the history so far, and I can't say I approve. People either coming down on the side of, well, it's all a fool's errand, we're never going to have quantum computers, the pessimist's idea, or downplaying the contribution of certain people. And I don't know why this happens. But I don't know why Popper is downplayed in the academy either. But these things happen. So regardless, here we have Feynman talking about how if you want to try and compute the behaviour of quantum mechanical objects, in other words, predict what's going to happen with them, it seems to be intractable. What's an example? Well, take an atom of some kind or other. If you just have to predict what's going to happen with the electron in a hydrogen atom orbiting its single proton, well, that seems pretty straightforward. After all, there's only two objects there. There's the proton and the electron. And there's only a couple of forces, so to speak, the electrostatic force of attraction between the positive nucleus and the negative electron, and for want of another term, the exclusion principle, or Heisenberg's uncertainty principle, whatever you want to refer to it, the quantum mechanical effect that causes the thing to not spiral into the nucleus, the electron into the nucleus, I should say. So we've got the balancing act between these two forces. Okay, very well. But as soon as you start to deal with something more complicated like the helium atom, well, things begin to spiral out of control into complexity. Now you have 2 electrons and 2 protons, and you have some neutrons as well. Now, one of those protons is going to have an effect on one of the electrons, and one of the electrons is going to have an effect on one of those protons. So there you have something like the hydrogen atom, except that you've got the 2 electrons. They're each going to have an effect, each one upon the other, and they're also going to have an effect each upon the 2 protons that are in the nucleus. So this is already becoming exponentially more difficult in terms of predicting where those electrons are going to be moment to moment, insofar as you were able to do that at all. Never mind when we get to carbon. Carbon's number 6 on the periodic table. So now you've got 6 electrons, and not only are they not at the same distance from the nucleus, because now they're in 2 shells, if you like, they're in different energy levels, they're at different distances from the nucleus, but having 6 of them, each of them having an effect one upon the other and upon all the objects in the nucleus, we're rapidly spiraling out of control in terms of trying to predict what any one of them is going to do from moment to moment, let alone the entire ensemble. And we're just still talking single atoms, never mind molecules. Okay, so this is the difficulty that Feynman was envisaging, especially if you're trying to compute these things using a classical computer. Okay, so let's go back to the book and see what David has to say about this. He writes, quote, "One reason why the significance of this had not been appreciated is that no one expected the computer prediction of interesting physical phenomena to be especially easy. Take weather forecasting or earthquake prediction, for instance. Although the relevant equations are known, the difficulty of applying them in realistic situations is notorious. This has recently been brought to public attention in popular books and articles on chaos and the butterfly effect. These effects are not responsible for the intractability that Feynman had in mind, for the simple reason that they occur only in classical physics, that is, not in reality, since reality is quantum mechanical." Pausing there, my reflection on this. This idea that the weather is difficult to predict, it kind of seems to be an intractable problem. Everyone knows this phenomena. Even recently it was brought home to me that, we have stretches of good weather here in Sydney, and they seem to do a good job of predicting long stretches of good weather. But then, one particular day, it was only a few weeks ago, we had a thunderstorm that no one predicted, and it was quite a severe thunderstorm as well. It just can't seem to come out of the clear blue sky. The meteorologists did not predict it. There you go. But the idea about earthquakes, I remember studying geophysics, and it was back in 2012, and just by coincidence, as I was studying this stuff, there was an earthquake in Italy, La Aquila, and it was a huge earthquake there. Now, devastating as it was, one of the more interesting things to come out of that earthquake was the seismologists in Italy were convicted of manslaughter for not accurately predicting the earthquake. You can look this up. 2012, conviction of seismologists in Italy. The government expected that they should have been able to predict the earthquake, but, as we were studying at the time, and the academics at Macquarie University, where I was studying this at the time, were readily able to explain, we simply can't predict earthquakes. We don't know how to do this. You can have all the fancy sensors that you like connected to plates and so on and so forth to detect whether or not they're moving slightly, but slight movements don't indicate that large movements are about to happen. It is very difficult to tell when you've got huge solid objects sliding past each other when they stick, and then it's called the stick-slip phenomena. When they stick, you don't know exactly when they're going to slip. We can't do this. We don't know how to actually predict when earthquakes are going to happen. So this was a remarkable event that scientists would actually be convicted for not doing the thing that hitherto is impossible for us to do given our state of knowledge and technology. There you go. Don't be a seismologist in Italy, I think, is the lesson there. But here in the chapter we have the first mention of this so-called butterfly effect or chaos. David's going to go into this. So let me read what David has to say about this, and I'll put my own spin on things here if you like. David goes on to say, quote, after saying, reality is quantum mechanical, but the butterfly effect itself is a classical phenomena. All right, quote, Nevertheless, I want to make some remarks here about chaotic classical motions, if only to highlight the quite different characters of classical and quantum unpredictability. Chaos theory is about limitations on predictability in classical physics, stemming from the fact that almost all classical systems are inherently unstable. The instability in question has nothing to do with any tendency to behave violently or disintegrate. It is about an extreme sensitivity to initial conditions. Suppose we know the present state of some physical system, such as a set of billiard balls rolling on a table. If the system obeyed classical physics, as it does to a good approximation, we should then be able to determine its future behaviour, say whether a particular ball will go into a pocket or not, from the relevant laws of motion, just as we can predict an eclipse or a planetary conjunction from the same laws. But in practice, we are never able to measure the initial positions and velocities perfectly. So the question arises, if we know them to some reasonable degree of accuracy, can we also predict to a reasonable degree of accuracy how they will behave in the future? And the answer is usually that we cannot. Pausing there, my reflection. Okay, so first let's deal with the billiard ball situation and really get a handle on what David's referring to here. If you were able to write down the equations of motion for the movement of billiard balls on a billiard table, which you can, very straightforward, classical equations of motion, then if one billiard ball is here and one billiard ball is here and you're shooting one billiard ball at the other, then what you want to know is precisely where this billiard ball is and exactly at what velocity its initial velocity is as it moves away from where it starts to where it's going to go. All right, here's the problem. Exactly where is it, so that when you strike it, you know precisely where you're going to hit it? Well, you might say it's at x equals 1 centimetre away from the edge of the billiard ball table. Okay, well, that's to a certain level of precision. Perhaps a more precise measurement, if you had a better ruler, would be 1.01 centimetres away from where the edge of the billiard ball table is. But if you had an even more precise measuring device, maybe lasers and so on and so forth, you'd find out it's 1.010001 centimetres away from the edge. And these differences, these very subtle differences, are going to change the precise angle at which you would want to hit that if you had some sort of ideal robot situation where you're going to be able to program this robot to use a pool cue to hit the ball exactly at a particular velocity when you want to hit it, where you want to hit it. Classically, there is no limit to how precise you'd want to become. And when you plug these numbers into the equations, and ever so slight, 1/1,000,000th of a difference between the precision of these two values is going to have a big effect on what actually happens. If you're off by the tiniest percentage, it's going to have a large effect, classically speaking, on where the billiard ball is going to go. And this is what we mean here, and this is what David means here, where he says, but in practice we are never able to measure the initial positions and velocities perfectly. That's both classically and in the quantum realm. Classically, there is no smallest amount of anything at all. So you can never get perfect precision. There's no such thing as perfect precision classically. You can only ever get more and more precise, asymptotically approach whatever the real position or the real quantity is that you're trying to measure. In the quantum realm, there is such a smallest amount. But just remember that in terms of space and time is governed by general relativity, which is a classical theory. So there is no smallest unit of space and time. There might very well be something called the Planck Time, Planck Length, which people make a big deal about. I've talked about on Talkcast before. That's more about what is the smallest unit of time and space that you can measure. But that is a very different question to what is the smallest unit of time, or what is the smallest interval of time, or the smallest interval of space that exists. And that is governed by general relativity. And as far as I know, general relativity says that you can just continue dividing up space-time into as smaller intervals as you like. Quantum theory says that things cannot be so divided up, but it is not a theory of space-time. So therefore, although it says that there's a limit to the smallest unit of space-time that you can measure, because our measuring devices have a fundamental limit built into them because of quantum theory, that doesn't mean that the continuous space and time that really exists according to general relativity actually has some sort of quantum element to it. We don't have the successor theory to quantum theory and to general relativity. Maybe a quantum gravity, if that thing ever arose, would tell us that there's a smallest unit of space-time, but we're not there yet. We don't know that. We have no such theory of that. nor do we even have an expectation that space-time should be quantized, even though so many particle physicists seem to think that this has to be the case. It doesn't have to be the case. There could be another theory altogether, a third theory that stands apart from quantum theory, from general relativity, and is just different altogether, subsuming both of them and not quantizing space. We don't know. We're in the position where we don't know. But if we're going to take our best theories now, seriously now, as explanations of reality now, we have to insist that there is no smallest unit of time and there is no smallest unit of space. Even if we are limited to exactly how precise our measurements of these things can be, we cannot measure the positions and velocities of anything perfectly, as David says there. You can observe yourself the exquisite susceptibility to differences in initial conditions for a approximately classical system, although nothing is classical, of course. We know that everything is quantum, except for gravity. If you look at the thing called the double pendulum, if you've never seen a double pendulum before, I'll put one up on the screen. A double pendulum is one pendulum attached to the other, while a single pendulum is perfectly predictable, as we like to say, approximately perfectly predictable. The double pendulum, if you change the starting point of it, then what it does over time is very different. Each time you run the thing, you get a different trajectory. It appears to demonstrate what is called chaos. But this is not genuine chaos. There's no such thing as genuine chaos. For chaos to be chaos, I suppose it would have to be completely indeterminate. You wouldn't be able to, it would be governed by nothing. It would be ungovernable. And not governed by any physical laws. But there's no such thing in this universe. So it displays extremely complex behaviour, but not chaotic behaviour, just to an approximation. Now, what is this butterfly effect? What is this thing, this butterfly effect? A lot of popular science makes a huge deal about the butterfly effect as if it's a real thing. It's entered the zeitgeist, you know. You yourself in your personal life make one small change and it has this amplification effect, causing big things to happen in the lives of others or in yourself at some later point. Okay. Let's just read what David has to say about the butterfly effect, and I'll have some reflections upon this. He goes on to say, quote, "So the question arises, if we know them, the initial conditions, to some reasonable degree of accuracy, can we also predict to a reasonable degree of accuracy how they will behave in the future, they being these systems? And the answer is usually that we cannot. The difference between the real trajectory and the predicted trajectory, calculated from slightly inaccurate data, tends to grow exponentially and irregularly, chaotically, with time, so that after a while the original slightly imperfectly known state is no guide at all to what the system is doing. The implication for computer prediction is that planetary motions, the epitome of classical predictability, are untypical classical systems in order to predict what a typical classical system will do after only a moderate period. One would have to determine its initial state to an impossibly high precision. Thus it is said that in principle the flap of a butterfly's wing in one hemisphere of the planet could cause a hurricane in the other hemisphere. The infeasibility of weather forecasting and the like is then attributed to the impossibility of accounting for every butterfly on the planet." End quote. So there we have it. So classically, we would need to have an impossibly high precision in terms of our values that we want to plug into our equations for the initial conditions of any attempt to predict what's going to happen for the evolution of a particular system over time, governed by those equations of motion. We've got to put some numbers in. The numbers can't be arbitrary. They have to be measured. Our measuring devices are limited. But even if we had super precise measuring devices, it wouldn't matter how super precise they are, unless they were infinitely precise. There would always be a difference between what is measured and what is real. You could measure something, the length of something, down to the 15th decimal place. I guess impossible given any real life measuring device, the 15th decimal place. But in reality, the decimal places go on forever. And so there's an infinite difference in precision between reality, which is infinitely precise, and your measurement of it, which isn't. And that difference is always going to be amplified, magnified by the evolution of the system over time. As time goes on, the differences become more and more pronounced over time. And so therefore your prediction becomes less and less accurate over time. Okay, so that's one thing. As David goes on to say, and this is really where I want to get to for the punchline here, he says, quote, having just talked about how, the butterfly flaps its wings on one side of the planet and on the other hemisphere you get a hurricane. This could happen classically. I'll get to why in a moment, but it can't happen in the real world, and I'll get to why. David says, quote, however, real hurricanes and real butterflies obey quantum theory. not classical mechanics. The instability that would rapidly amplify slight misspecifications of an initial classical state is simply not a feature of quantum mechanical systems. In quantum mechanics, small deviations from a specified initial state tend to cause only small deviations from the predicted final state. Instead, accurate prediction is made difficult by quite a different effect. Pausing there in my reflection. Before I get onto that quite different effect, let's talk about why the butterfly effect doesn't exist in real life. Here's why it doesn't exist. Classically speaking, if the butterfly flaps its wings here in my room, then as you get further and further away from the butterfly's wings, the strength with which the air has been disturbed becomes less and less and less. If you're right next to the butterfly flapping its wings, then you can feel the little flap of the butterfly's wings. But if you're now 1 metre away, maybe you can barely feel it at all. Of course, in real life, you'd never be able to feel it. But let's say you're super sensitive. Okay, 1 metre away, you can barely feel it. 10 metres away, hardly any hope. But classically speaking, that just means you can't feel it. It doesn't mean there's not actually been disturbance of the air. The air will be disturbed by the butterfly's wings no matter how far away you are from it. It's like ripples of water spreading out from where you drop a stone in a lake. Those ripples become ever more faint, ever smaller. Right near where the stone has been dropped, yeah, big wave. But now that energy is being spread out over more and more area of the top of the lake. And the wave, therefore, gets smaller and smaller, diminishing in amplitude, as we say. So too with the butterfly's wings. The disturbance of the air gets ever smaller and smaller without limit. Without limit. That's classically speaking. But the real world operates according to quantum theory. And there is, in quantum theory, a smallest disturbance possible. A smallest amount of energy. The quantum of energy. There's photons. Classically speaking, light, for example, can be turned down ever more dimly, and we've talked about this here in the Fabric of Reality in the chapter on shadows. Turn down the dimness of a light, classically speaking, and you never get to a smallest amount of light. There is no such thing as the smallest amount of light. Classically speaking, there's no such thing as the smallest amount of water. You don't get to a quantum of water. But we know now there is a smallest amount of water. It's called the molecule of water. There's a quantum of water, the smallest amount of water. In the same way, there's a smallest amount of light. It's called the photon of light. There's the smallest amount of energy, the photon of energy. So, classically speaking, although the flap of the butterfly's wings never decays to zero, quantum theory says there will come a point at which you get a smallest disturbance of the air which will not be able to disturb any air any further. This reminds me of a similar analogy. We can talk about this, the phenomena of a supernova going off somewhere in another galaxy. Okay, somewhere in another galaxy. Now, if you're on a planet orbiting a star that's near to that supernova that's having gone off, you better believe that the energy of that supernova is going to cause you serious disturbances. The energy of those photons is going to have physical effects upon the planet that you're on. They're blowing away the atmosphere. Literally, the photons are so energetic, they can just split apart the molecules of gas in the air of your atmosphere. Okay, so it's going to have severe physical consequences. Now, if there's a supernova that goes off in our galaxy, on the other side of our galaxy, as has happened in living memory, I think 1987A, that might have been in the Magellanic Clouds. Anyway, you can imagine that so long as the supernova is far enough away, still within our galaxy, it can still have some minor physical effects. Maybe the photons of light are so energetic that when they strike the atmosphere here, they can ionize some of the molecules of air, ionizing some of those molecules of air. How does this physically happen? Well, what physically happens is the photons arrive here at Earth, they crash into, they have physical collisions with the electrons orbiting the nuclei of the molecules of air. And when they do, those photons hit those electrons, they bump them up to another energy level. The photon gets absorbed, physically bumps the electron up to a higher energy level. It's got now more energy. And then that electron can fall down from the energy level, the new energy level that it's got, and release another photon. So that's a physical effect. That's a physical effect that can happen given the energy of the photon coming in. Now I've talked about this on Talkcast before, that there are sort of these three things that can happen in theory if a photon interacts with an atom. And the three things are, one, the photon has so much energy that when it strikes the atom, hitting the electron, being absorbed by the electron, it has so much energy, it physically knocks the electron out of the atom. That's called ionizing the atom. So a photon can have that much energy, ionizing radiation, so to speak. It can just have so much energy it causes a real physical effect of removing the electron from the atom. It can have that lesser effect that I just mentioned now, where it doesn't knock the electron entirely out of the atom, but instead the photon comes in, it gives its energy to the electron, and it causes it to rise up 1, 2, 3, 10 energy levels. But it's still orbiting the nucleus, but now it's got a lot more energy. And so it's orbiting the nucleus at this higher energy, and that's unstable. So what it tends to do is the electron tends to fall down. It can either fall down in one go or it can cascade down one step at a time. And each time it comes down an energy level, it releases photons. And so this produces photon emission. It produces the emission of photons. Right, so that could happen. But on quantum theory, what can also happen is nothing at all, except the vibration of the atom a little bit. In other words, the photon that comes in can have insufficient energy to cause the electron to move up an energy level. It will be absorbed, but it causes the thermal energy of the atom to increase. But otherwise, there's no movement of the electron. The electron isn't changed in place. There's a minimum possible energy. There's a threshold of energy, the quantum of energy that is required to be delivered to an electron orbiting a nucleus in order to cause it to rise up to the next energy level. And if that minimum threshold is not exceeded, there will be no movement of the electron from one energy level to the other. It just won't happen. And this fundamentally is why the butterfly effect isn't a real thing. There is a minimum flap, a minimum amount of energy coming from those butterfly wings, which, if the threshold is not exceeded, will not cause the air to continually be disturbed all the way from one hemisphere to the other. We kind of know this intuitively, that this is what really must go on, that disturbances of air in one place don't actually reach to another place. Now, classically, that doesn't happen. As we say, that you can have movements of air all over the place that never decay to zero and can come together to amplify each other in a huge wave of motion, which we call a hurricane of some sort, okay? In theory, that's what could happen, classically. But happily, our world doesn't operate classically. It operates via quantum laws of physics, where things can decay to a minimum amount, Classically, they do not decay to a minimum amount ever, and so therefore they can be carried, these influences, these effects can be carried from one side of the planet to the other. And hence you've got this thing called chaos theory, or the butterfly effect. So that's one aspect of the butterfly effect. The other aspect of the butterfly effect, closely related, is this idea that if the butterfly flaps its wings, maybe nothing happens, classically speaking, on the other side of the world, or maybe it causes a hurricane. These are two huge differences in the state of the world at the end product, the final outcome, given the initial conditions. Okay, the butterfly slightly moves its wings in this direction rather than that direction, hurricane or not. Okay, that means that classically speaking, it's impossible to predict certain classical systems, the evolution of certain classical systems, just as it's so difficult to predict what's going to happen with the double pendulum. You can't measure precisely the starting point of the double pendulum, which is what you need to do. You need to measure it exquisitely precisely in order to predict what the trajectory will be from moment to moment. You can't do that, and so therefore the final outcome, what the trajectory is going to be, is unknown to you, even if you have the initial conditions to some approximation. And a perfect knowledge of the laws of motion, classically speaking. Of course, they're not classical in real life. Okay, that aside. David has just said, accurate prediction under quantum theory is made difficult by quite a different effect. So let's talk about that. He goes on to say, quote, "The laws of quantum mechanics require an object that is initially at a given position, in all universes, to spread out in the multiverse sense. For instance, a photon and its other universe counterparts all start from the same point on a glowing filament, but then move in trillions of different directions. When we later make a measurement of what has happened, we too become differentiated, as each copy of us sees what has happened in our particular universe. If the object in question is the Earth's atmosphere, then a hurricane may have occurred in 30% of universes, say, and not in the remaining 70%. Subjectively, we perceive this as a single, unpredictable or random outcome, though from the multiverse point of view, all the outcomes have actually happened." Pausing there, my reflection. This is so crucial to appreciate. There is no randomness in quantum theory. Quantum theory is not a theory of randomness. It is a theory of objective determinism. Everything is determined by the quantum laws of physics across the multiverse. But you do not occupy all the multiverse. You occupy some set of universes. Subjectively speaking, you don't know which universe you're in from moment to moment, let alone where you're going to be in the future. And so, subjectively, things appear to be random. Subjectively, things appear to probably happen, but nothing probably happens. Things actually are going to happen to you. Nothing is random just because you can't predict what's going to happen. As David says there, you've got these photons coming from the filament. They're all coming from the same place in the filament, but because there is a range of possible places where they can go then, once they've left the filament, then you're going to have different effects in different universes, but all of them obtain. Okay, all of these different possible trajectories of the photon leaving the filament are going to happen across the multiverse. And in some of those, you're going to have hurricanes, and in some you're not going to have hurricanes. And he said there, 30% of universes have a hurricane and 70% don't. So that's perfectly determined. That's not random. There's nothing random about that. But you, being in a universe where you don't know, and you cannot know what universe you're in, are going to perceive things as random, or at least unpredictable. Random would be, of course, even given 30% and 70%, that something else entirely happens. That would be true randomness, right? Okay, so it wouldn't even obey those proportions. There would be no law whatsoever, which is why, by the way, David puts random in scare quotes here. There is no random. All the physically possible outcomes, by physically possible we mean physically possible as determined by the laws of quantum theory. David says, quote, "This parallel universe multiplicity is the real reason for the unpredictability of the weather. Our inability to measure the initial conditions accurately is completely irrelevant. Even if we knew the initial conditions perfectly, the multiplicity and therefore the unpredictability of the motion would remain." Pausing there, my reflection. Just to emphasize that. Even if we could, and we can't, but even if we could, determine precisely from where, in other words, our x, our position, from where the photons were coming to perfect precision, that would not mean that we would be able to determine where any individual photon was going to go. Maybe it's determined perfectly well that if you start at point X, then half of the time you go left and half of the time you go right. So that could be a situation in which we're in. But the laws would also tell us that you can't tell which proportion of the universe you happen to be, the multiverse you happen to be in. Are you in the 50% of universes where it goes left, or are you in the 50% of universes where it goes right? You don't know, even though it's perfectly determined, and even though you have a perfect understanding of where that photon is being emitted from. So at that point, it's not down, the unpredictability is not down to being able to measure something or not. It's down to the fact that, subjectively speaking, you occupy only part of the multiverse, not the entire thing. David goes on to say, and on the other hand, in contrast to the classical case, an imaginary multiverse with only slightly different initial conditions would not behave very differently from the real multiverse. It might suffer hurricanes in 30.0000001% of its universes and not in the remaining 69.999999%. The flapping of butterflies' wings does not, in reality, cause hurricanes because the classical phenomenon of chaos depends on perfect determinism, which does not hold in any single universe. Pausing there, my reflection. Perfect determinism does not hold in any single universe. Any single universe. Perfect determinism holds in reality, in physical reality, but physical reality is the multiverse. But in any single universe, approximately speaking, the single universe is emergent. The fundamental thing is the multiverse. It's physical reality. Emerging from that are these approximations that we can talk about called single universes. And these approximations of being observers, us, people inside of those single universes approximately. We actually know that they are uncountably infinite number of fungible instances of ourselves in these universes. When you're in these single universes, you can't determine what's going to happen from moment to moment in your universe. You can't predict. It appears to be random. And so that's why we say perfect determinism does not hold in any single universe. Let's keep going. David says, quote, "Consider a group of identical universes at an instant at which in all of them a particular butterfly's wings have flapped up. Consider a second group of universes which at the same instant are identical to the first group except that in them the butterfly's wings are down. Wait for a few hours. Quantum mechanics predicts that unless there are exceptional circumstances, such as someone watching the butterfly and pressing a button to detonate a nuclear bomb if it flaps its wings, the two groups of universes nearly identical at first are still nearly identical. But each group within itself has become greatly differentiated. It includes universes with hurricanes, universes without hurricanes, and even a very tiny number of universes in which the butterfly has spontaneously changed its species through an accidental arrangement of all its atoms, or the sun has exploded because all its atoms bounce by chance towards the nuclear reaction at its core. Even so, the two groups still resemble each other very closely. In the universes in which the butterfly raised its wings and the hurricanes occurred, those hurricanes were indeed unpredictable, but the butterfly was not causally responsible. For there were near-identical hurricanes in universes where everything else was the same, but the wings were lowered. It is perhaps worth stressing the distinction between unpredictability and intractability. Unpredictability has nothing to do with the available computational resources. Classical systems are unpredictable, or would be if they existed, because of their sensitivity to initial conditions. Pausing there, my reflection, just remember. So why is this unpredictability there? Because of the initial conditions, the sensitivity to the initial conditions? Because you cannot measure the initial conditions to infinite precision, which is what you would need in order to predict how the system is going to evolve over time. You need two things to be able to predict how the system is going to evolve over time. Perfect understanding of the laws of motion, presume you have those and they're classical, but also perfectly precise, accurate statements of the initial conditions to the infinite number of decimal places as to where the position of that object is and its initial velocity. Okay, you need those two things to perfect precision. And if you're off by any amount at all, that degree by which you're off is going to magnify itself for every time t equals 1, t equals 2, t equals 3, t equals 4. It's just going to diverge from reality over time. And hence, that is why classical systems are unpredictable, because they're sensitive to the initial conditions. And if you think the object is here, but in fact it is fractions of a millimeter to the left or to the right, then how you predict things are going to evolve is going to be very different to what they're going to evolve like in reality. Okay, David goes on to say, quote, quantum systems do not have that sensitivity. Okay, pausing there. Why not? Well, because there is no such thing as having infinitely precise measurements of physical quantities there. There is a smallest possible amount that you can get down to. But it's going to be a range of things. It's different. This is the Heisenberg uncertainty principle comes in here. You can't measure things to infinite precision. In classical theory, you can't anyway, because there's a limit to, obviously, how precise your measuring device is. But here, this has got nothing to do with measuring devices. Here, this has to do with, in reality, the object itself is spread out in space. It really doesn't occupy a single position. In classical physics, it does. It's there at a particular point x, but you can't measure it to that perfectly precise point x. Quantum theory says, never mind trying to measure it at a particular point x, it's spread out in space. It's spread out in time, spread out in terms of energy, and so on and so forth. So the object is spread out in space. This is not to say, by the way, this is not to say that space itself is spread out. This is different, okay? The atom or the electron or whatever the particle is that's in space, it is spread out in space, okay? That is, and it's spread out in time as well. This is a very different kind of thing to saying time itself has a limit to its precision, or that space itself has a limit to its precision. No, again, theories of space and time, the explanation of space and time is general relativity, not quantum theory. But where an object happens to be in space and time does come down to our understanding of how it is we observe these things in reality, and that is quantum theory. As David says, quote, quantum systems do not have that sensitivity, but are unpredictable because they behave differently in different universes, and so appear random in most universes. In neither case will any amount of computation lessen the unpredictability. Intractability, by contrast, is a computational resource issue. It refers to a situation where we could readily make the prediction if only we could perform the required computation, but we cannot do so because the resources required are impractically large. In order to disentangle the problems of unpredictability from those of intractability in quantum mechanics, we have to consider quantum systems that are, in principle, predictable. Quantum theory is often presented as making only probabilistic predictions. For example, in the perforated barrier and screen type of interference experiment described in Chapter 2, the photon can be observed to arrive at anywhere in the bright part of the shadow pattern. But it is important to understand that for many other experiments, quantum theory predicts a single, definite outcome. In other words, it predicts that all universes will end up with the same outcome, even if the universes differed at intermediate stages of the experiment, and it predicts what that outcome will be. In such cases, we observe non-random interference phenomena. An interferometer can demonstrate such phenomena. This is an optical instrument that consists mainly of mirrors, both conventional mirrors and semi-silvered mirrors. Okay, pausing there, my reflection. Now, I have spent hours explaining this on Topcast in previous episodes. So I will read this section, but I'm going to gloss over it. I'll have some remarks to say, but I urge you, if you don't understand this or feel as if you don't appreciate it as I'm going through it, to go to the multiverse section of The Beginning of Infinity, in particular my videos here that I'll put up on the screen, where I deal with this at some length, and try to explain how this sort of thing really works. And in those videos, I point to several other resources as well, not to mention the great David Wallace, who has a wonderful exposition of this particular experiment online on YouTube. So, yeah, well worth watching that. And it's well worth trying to get your head around this kind of experiment, the Mach-Zehnder interferometer, as it's so called, if you want to understand some of the deep mysteries behind quantum theory. Anyway, let's keep going. David writes, quote, "If a photon strikes a semi-silvered mirror, then in half the universes it bounces off, just as it would from a conventional mirror. But in the other half, it passes through as if nothing were there. A single photon enters the interferometer at the top left, as shown in this figure. In all the universes in which the experiment is done, the photon and its counterparts are travelling towards the interferometer along the same path. These universes are therefore identical. But as soon as the photon strikes a semi-silvered mirror, the initially identical universes become differentiated. In half of them, the photon passes through and travels along the top side of the interferometer. In the remaining universes, it bounces off the mirror and travels down the left side of the interferometer. The versions of the photon in these two groups of universes then strike and bounce off the ordinary mirrors at the top, right, and bottom left, respectively. Thus, they end up arriving simultaneously at the semi-silvered mirror on the bottom right and interfere with one another. Remember that we have allowed only one photon into the apparatus, and in each universe, there is still only one photon in there. In all universes, that photon has now struck the bottom right mirror. In half of them, it has struck from the left, and in the other half, it has struck it from above. The versions of the photon in these two groups of universes interfere strongly. The net effect depends on the exact geometry of the situation, but this figure shows the case where in all universes the photon ends up taking the rightward pointing path through the mirror, and in no universe is it transmitted or reflected downwards. Thus, all the universes are identical at the end of the experiment, just as they were at the beginning. They were differentiated and interfered with one another only for a minute fraction of a second in between. Pausing there, my reflection. So here we have the mystery of the multiverse, or the explanation of the multiverse, I really should say. If you're striking a semi-silvered mirror, then in 50% of the universes you go through and in 50% of the universes you bounce off. Right. But if you have this situation here, where you have a semi-silvered mirror at the end and all of the photons appear to come out in the one direction, the only possible explanation is that there's been interference. Interference caused by the photon travelling both paths. The only explanation is that there must have been a single photon which has now taken both paths of the apparatus to interfere with itself so that it comes out in just that one direction rather than going in both directions. After all, if that wasn't the case, then you should expect the thing to 50% of the time come to be transmitted through and 50% of the time to be bouncing off that second semi-silvered mirror. But that's not what happens. David's main point here is not to present yet another argument for the existence of the multiverse, although that's what I've just done, but rather to say that sometimes in quantum theory you can have perfectly predictable outcomes of experiments. Here is one such. Here is one such where we know that no matter what universe you're in, you're always going to see the photon go in this particular direction. Always. Okay, so there's no probabilistic stuff going on here at all. Okay, you know that the photon is coming out that direction because that's what the laws of quantum theory say is going to happen. And we can check it with experiment, and in fact, that's what happens. As David goes on to say, quote, "This remarkable non-random interference phenomenon is just as inescapable a piece of evidence for the existence of the multiverse as is the phenomenon of shadows. For the outcome that I have described is incompatible with either of the two possible paths that a particle in a single universe might have taken. If we project a photon rightwards along the lower arm of the interferometer, for instance, it may pass through the semi-silvered mirror like the photon in the interference experiment does, but it may not. Sometimes it is deflected downwards. Likewise, a photon projected downwards along the right arm may be deflected rightwards, as in the interference experiment, or it may travel straight down. Thus, whichever path you set a single photon on inside the apparatus, it will emerge randomly. Only when interference occurs between the two paths is the outcome predictable. It follows that what is present in the apparatus just before the end of the interference experiment cannot be a single photon on a single path. It cannot, for instance, be just a photon travelling on the lower arm. There must be something else present, preventing it from bouncing downwards, nor can there just be a single photon travelling on the right arm. Again, something else must be there preventing it from travelling straight down, as it sometimes would if it were there by itself. Just as with shadows, we can construct further experiments to show that the something else has all the properties of a photon that travels along the other path and interferes with the single photon we see, but with nothing else in our universe." Pausing there, my reflection. Yes, and so this is why we also say that these other interpretations that exist that try and get around explaining this kind of thing by recourse to, well, it's actually another photon travelling along there, and instead saying things like, well, there's a wave, there's a pilot wave that is transmitted out. That wave has all the complexity of the multiverse. It has all the complexity of another photon interfering with the photon that we have transmitted through the apparatus. And so long as you're postulating an entity with all the complexity of physical reality in order to explain the outcome of the experiment, then you're invoking the multiverse. You're just saying that reality consists of these other things that we can't observe, but which are causally having an effect upon the things we do observe. You can't actually directly observe the so-called wave or pilot wave or whatever you want to call it travelling through the apparatus. We say, well, you can't directly observe the photons travelling upon both arms, but the most parsimonious way of understanding what's going on is there must be two things travelling along the arms. After all, we can observe one photon going into the apparatus, and we know what happens when it hits a semi-silvered mirror. 50% of the time it goes through, 50% of the time it bounces off. But only if something goes along both those arms can we actually have interference. So why not just presume that two photons are going along those arms? Why two photons? Because the universes have differentiated themselves at that point into photons along the top arm and along the down, through the transmitted arm and through the bouncing off arm. David goes on to say, quote, "Since there are only two different kinds of universe in this experiment, the calculation of what will happen takes only about twice as long as it would if the particle obeyed classical laws, say if we were computing the path of a billiard ball. A factor of 2 will hardly make such computations intractable. However, we have already seen that multiplicity of much larger degree is fairly easy to achieve. In the shadow experiments, a single photon passes through the barrier, in which there are some small holes, and then falls on a screen. Suppose that there are 1,000 holes in the barrier. There are places on the screen where the photon can fall, does fall in some universes, and places where it cannot fall. To calculate whether a particular point on the screen can or cannot ever receive the photon, we must calculate the mutual interference of 1,000 parallel universe versions of the photon. Specifically, we have to calculate 1,000 paths from the barrier to the given point on the screen, and then calculate the effects of those photons on each other, so as to determine whether or not they are all prevented from reaching that point. Thus, we must perform roughly 1,000 times as much computation as we would if we were working out whether a classical particle would strike the specified point or not. The complexity of this sort of computation shows us that there is a lot more happening in our quantum mechanical environment than literally meets the eye. And I have argued, expressing Dr. Johnson's criterion for reality in terms of computational complexity, that this complexity is the core reason why it does not make sense to deny the existence of the rest of the multiverse. Pausing there, my reflection. Right. So you want to predict where a particular photon ends up on the screen in this interference experiment, and you're just firing one at the apparatus at a time. then you have to account for all the possible paths it has taken. If you're predicting it, if you're really trying to predict where this individual photon is going to go, you have to invoke the existence of all these other entities. Computationally speaking, you're required to postulate the real existence of these other things. So that's the computational argument for the existence of the multiverse. The only way of predicting what's going on is to postulate the existence of things you can't observe. More than meets the eye, which really must be there, but they're not going to enter your eye. Okay, as David goes on to say, quote, "But far higher multiplicities are possible when there are two or more interacting particles involved in an interference phenomenon. Suppose that each of the two interacting particles has, say, 1,000 paths open to it. The pair can then be in 1,000,000 different states at an intermediate stage of the experiment. So there can be up to 1,000,000 universes that differ in what this pair of particles is doing. If 3 particles were interacting, the number of different universes could be 1,000,000,000, for 4, 1,000,000,000,000, and so on. Thus, the number of different histories that we have to calculate if we want to predict what will happen in such cases increases exponentially with the number of interacting particles. That is why the task of computing how a typical quantum system will behave is well and truly intractable." End quote. Worth repeating. You've got 2 particles. They're interacting. There could be 1,000 paths open to these 2 interacting particles, David says. Then that means that if you're trying to predict what's going to happen at some point in the future, then you're going to have to consider 1,000,000 different states in the future to predict where it's going to end up. That's just for a pair of particles with 1,000 different paths open to this pair of particles that are interacting. But if you've got 3 particles now, similarly, it could be 1,000,000,000 different universes, for 4, 1,000,000,000,000. This is what we mean by intractable. The quantum system's behaviour is well and truly intractable because for every particle you add, you're multiplying the number of outcomes by 1,000. By 1,000. That's pretty intractable. Difficult to compute. The computational resources are spiralling out of control. David says, quote, "This is the intractability that was exercising Feynman. We see that it has nothing to do with unpredictability. On the contrary, it is most clearly manifested in quantum mechanical phenomena that are highly predictable. That is because in such phenomena, the same definite outcome occurs in all universes. But that outcome is the result of interference between vast numbers of universes that were different during the experiment. All this is in principle predictable from quantum theory and is not overly sensitive to the initial conditions. What makes it hard to predict that in such experiments the outcome will always be the same is that doing so requires inordinately large amounts of computation. Intractability is in principle a greater impediment to universality than unpredictability ever could be. I have already said that a perfectly accurate rendering of a roulette wheel need not, indeed should not, give the same sequence of numbers as the real one. Similarly, we cannot prepare in advance a virtual reality rendering of tomorrow's weather, but we can, or shall one day be able to, make a rendering of weather, which, though not the same as the real weather conditions prevailing on any historical day, is nevertheless so realistic in its behaviour that no user, however expert, will be able to distinguish it from genuine weather. The same is true of any environment that does not show the effects of quantum interference, which means most environments. Rendering such an environment in virtual reality is a tractable computational task. However, it would appear that no practical rendering is possible for environments that do show the effects of quantum interference. Without performing the exponentially large amounts of computation, how can we be sure that in those cases our rendered environment will not do things which the real environment strictly never does because of some interference phenomenon? It might seem natural to conclude that reality does not, after all, display genuine computational universality, because interference phenomena cannot be usefully rendered. Feynman, however, correctly drew the opposite conclusion. Instead of regarding the intractability of the task of rendering quantum phenomena as an obstacle, Feynman regarded it as an opportunity. If it requires so much computation to work out what will happen in an interference experiment, then the very act of setting up such an experiment and measuring its outcome is tantamount to performing a complex computation. Thus, Feynman reasoned it might, after all, be possible to render quantum environments efficiently, provided the computer were allowed to perform experiments on a real quantum mechanical object. The computer would choose what measurements to make on an auxiliary piece of quantum hardware as it went along and would incorporate the results of the measurements into its computations. The auxiliary quantum hardware would in effect be a computer too. For example, an interferometer could act as such a device, and like any other physical object, it can be thought of as a computer. We would nowadays call it a special purpose quantum computer. We program it by setting up the mirrors in a certain geometry and then projecting a single photon at the first mirror. In a non-random interference experiment, the photon will always emerge in one particular direction determined by the settings of the mirrors, and we can interpret that direction as indicating the result of the computation. In a more complex experiment with several interacting particles, such a computation could easily, as I have explained, become intractable. Yet since we could readily obtain its result just by performing this experiment, it is not really intractable after all. We must now be more careful with our terminology. Evidently, there are computational tasks that are intractable if we attempt to perform them using any existing computer, but which would be tractable if we were to use quantum mechanical objects as special purpose computers. Notice that the fact that quantum mechanical phenomena can be used to perform computations in this way depends on their not being subject to chaos. If the outcome of computations were an inordinately sensitive function of the initial state, programming the device by setting it in a suitable initial state would be an impossibly difficult task. Using a quantum auxiliary device in this way might be considered cheating, since any environment is obviously much easier to render if one has access to a spare copy of it to measure during the rendering. However, Feynman conjectured that it would not be necessary to use a literal copy of the environment being rendered, that it would be possible to find a much more easily constructed auxiliary device whose interference properties were nevertheless analogous to those of the target environment. Then, a normal computer could do the rest of the rendering, working through the analogy between the auxiliary device and the target environment, and Feynman expected that would be a tractable task. Furthermore, he conjectured, correctly as it turned out, that all the quantum mechanical properties of any target environment could be simulated by auxiliary devices of a particular type that he specified, namely an array of spinning atoms, each interacting with its neighbours. He called the whole class of such devices a universal quantum simulator. But it was not a single machine, as it would have to be in order to qualify as a universal computer. The interactions that the simulator's atoms would have to undergo could not be fixed once and for all, as in a universal computer, but would have to be re-engineered for the simulation of each target environment. But the point of universality is that it should be possible to program a single machine, specified once and for all, to perform any possible computation, or render any physically possible environment. In 1985, I proved that under quantum physics, there is a universal quantum computer. The proof was fairly straightforward. All I had to do was mimic Turing's constructions, but using quantum theory to define the underlying physics instead of the classical mechanics that Turing had implicitly assumed. A universal quantum computer could perform any computation that any other quantum computer, or any Turing-type computer, could perform, and it could render any physically possible environment in virtual reality. Moreover, it has since been shown that the time and other resources that it would need to do these things would not increase exponentially with the size or detail of the environment being rendered, so that the relevant computations would be tractable by the standards of complexity theory. Pausing there, my reflection. And that's where we'll end the readings for today. It's a nice place to end, where David Deutsch has mentioned his own contribution to the field of quantum computation, proving that there is such a thing as the universal quantum computer in 1985. And this is why many of us give him the credit for laying the foundations for the entire field and really setting the scene for the industry. That is the multi-billion-dollar multinational search for these universal quantum computers. We don't have them yet, but they're coming. They're coming. And anyone saying they're not coming is just a pessimist in the literal sense, saying that some problem isn't soluble. For no good reason, because we know the laws of physics permit these things, so it's just a matter of knowing how, fixing the engineering. And I like how David says, proof of genius, I suppose, where he says here, the proof was fairly straightforward. For someone like him. Someone creative enough, I suppose. Yes, but of course, go to his website where that seminal paper is there. That is an important historic document, that paper, which I'll put up on the screen here, laying the foundations, as I say, for quantum computation, the entire field. And this computer, this device, that, as David says there, can do the work of any other computer, quantum or classical, but importantly, can do the work of any of those devices efficiently. Okay, it's able to do many tasks that would take a classical computer longer than the age of the universe. Okay, it would be intractable for a classical computer. It makes these things tractable. It can do some of these things like simulating quantum systems, factorizing numbers, cracking codes, which is what we'll get into next time. Actually, we'll talk a little bit about RSA, we'll talk about Shor's algorithm, and talk about some of the practical applications of these quantum computers. But until then, bye-bye.